This is the last video for section 5, and in it we're going to tie together the previous 6 videos. We will manage to tie together where the electron is, electron configuration and Aufbau diagrams, and light with frequency and wavelength and energy. And this is in a technique called atomic spectroscopy, or the atomic spectra, which is sometimes known as elemental fingerprinting, because each element has a very specific pattern in the method that we're going to discuss. So whether you like neon lights or fireworks or glow sticks, it turns out that the production of color for each of these follows the same rules and actually the same mechanism. And it comes down to where is the electron. So let's take a hydrogen atom, because hydrogen is the simplest atom out there. It has one proton, and around the proton are the various energy levels. The further away from the nucleus, the more energy involved with the electron, and the electron is usually in the first energy level. But it is possible to move the electron to a different energy level. You can move it from the first to the second energy level, and then have it go back to the first energy level. And then you can have it go to the third energy level, and it could drop back down to the second energy level, or it could go back to the first energy level. Let's start with the electron in the first energy level. If you wanted to move to a second or third energy level, if you wanted to move to the second energy level, since the second energy level is a higher energy level, you have to put in some energy. This can be from friction, this can be from chemicals, this can be from an explosion, it can be from electricity. You have to put energy into the atom. When it does that, it jumps from the first energy level, in this case, to the second energy level, and it takes a very specific amount of energy to do that, and that amount of energy is called a quanta. And the interesting thing is that when you go from the first energy level to the second energy level, the electron winks out of existence in the first energy level and winks into existence in the second energy level, but it never, ever, ever exists in between the two. That is called a quantum leap. When it makes the quantum leap back to the first energy level, that quantum energy must be released, and it is given up as a wavelength of light, h nu. If you happen to jump to the third energy level, it will take even more energy. And when you drop back to the first level, you'll release that same amount of energy, but it will be different energy. Different energies means different frequencies. Different frequencies mean different wavelengths. Different wavelengths means different colored lights being given off. Now, if you happen to take a tube of hydrogen gas and run a little electricity through it, you get this nice purplish type glow. But if you take that purple light and guide it through a prism, it will separate into various colors, just like white light does when you put it through a prism. But instead of giving a complete rainbow, what you get are these types of colors of light. You see sort of a pinkish, a bluish, a greenish, and a reddish, each at a different wavelength, because each has a different frequency, which means each has a different energy. And these represent the various jumps from higher levels to lower levels. It could be, for example, the 410 may be from the fourth energy level to the second energy level. The 434 may be from the third to the first, so on and so forth. And this splaying out of the actual colors is called, for hydrogen, the hydrogen emission spectrum, and in general, the elements emission spectrum. So let's compare hydrogen to helium. Hydrogen has one proton, one electron. Helium has two protons, two electrons, and their energy levels will be at different distances from each other and from the nucleus. That means it takes different energy to bump the electron. So should you decide to put energy into the system and raise the electron to the third energy level, the amount of energy needed for hydrogen is different for helium. When you drop back down, different amounts of energy will be released. Since nu 1 does not equal nu 2, lambda 1 cannot equal lambda 2, so the color of light for hydrogen is dropped from 3 to 1 will have to be different than the colored light from helium's drop to 3 to 1. So you run the electricity through the helium, and you get this color, different than that purplish color of hydrogen. And when you compare the spectrum, you notice that they don't match up at all. Each element has a unique spectrum. Take mercury. You may have seen mercury vapor lamps on the highway. When you look at its spectrum, it looks more like this. So the atomic spectrum for each individual element is essentially an atomic fingerprint. No two elements have the same atomic spectra. And here's a sample of 5 different types: beryllium, copper, manganese, strontium, and titanium. And you can see that if you're given an unknown, look at the top of the chart, by looking at the other 5, you can determine that the unknown is strontium. Why? Because each atomic spectra is unique for each element. So we're going to review. So number 1, electrons preferentially reside in the lowest possible energy state. They want to be in the lowest level they can be, and that's called the ground state. You can move an electron out of the ground state, but you need a very specific quantum of energy put into the atom. And now you say the atom is in the excited state. When the electron goes from a higher energy orbital to a lower energy orbital, a photon is released. The photon released has a very specific energy, so it has a very specific frequency and thus a very specific wavelength. And this is the very specific wavelengths of light released for a specific element is the atomic spectra of the element. The atomic spectrum is as unique as a fingerprint is in humans. So if you know the spectrum, you can figure out the element or elements that are present. And that completes section 5. In section 6, we're going to take electron configuration and use it to explain the periodic table and to begin to discuss periodic trends.